We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello students, myself Professor S.R. Bombaywala from the Electronics and Communication Engineering Department of S.N. Patel Institute of Technology and Research Center, UMRAKH. Today we are going to look at the topic of image enhancement in spatial domain, and basically we are going to now cover the topic of image sharpening. So going into it, what do you mean by sharpening filters? Now, in the previous lectures, we have looked at the smoothing filters, and the smoothing filters are nothing but basically the low pass filters, which are responsible for removing the fine details. And while removing these details, what they do is they are trying to introduce the blurs, and the most common smoothing filter that we have seen is the averaging filter. Now, sharpening filters are doing inverse of what the smoothing filter does. That means they are going to remove the blur and they are allowing the high frequency component to pass through. We have seen that the smoothing filters are responsible for passing the low frequency components, and hence they are the low pass filters. Similarly, the sharpening filters are the high pass filters. Now, we have talked previously that what are the low frequency and high frequency components of the image. So, just to get back to it, the image basically consists of a smooth part and the textured part. uh, you see that for creating a particular textures, the grayscales are changing very quickly. So whenever in the image, and if you find an area where the grayscales are changing very fast, we say that that particular area belongs to the high frequency components. Now, if you take a look around in your room, you can see that at the edges and the corners, when the ceiling meets the wall, you can see that there is a sharp change in grayscales. Even if the color of the ceiling and the wall is same, due to the lighting effect, you can see that there is a dark line which is forming at uh, the ceiling and the walls are meeting. And these are nothing but the edges. Similarly, in the corners, you can see that there is a dark point. So what this suggests that at these particular instances or at these particular points, the green scales are changing very fast, and hence they are known as the edges and the corners and represent the high frequency components. So the basic aim of the sharpening filters are to enhance or to detect these type of harsh means the high frequency components. So sharpening filters, just like the smoothing filters, can be uh, computed in 2 domains: the spatial domain as well as the frequency. What's the difference between spatial domain and frequency domain? Yeah. So in spatial domain, we are directly working on the pixels of the image, and in the frequency domain, we first of all take the transform, we go into the frequency domain, we do the processes, and then we come back to the spatial domain by using the inverse frequency transforms. Okay. So now, since we are talking about the differences in the grayscales of the objects, the sharpening filters are based upon the spatial differentiations. So in the following slides, we are going to see how the sharpening filters are calculated by using the spatial differentiation, how to calculate the spatial differentiation in 2 dimensions, and so on. But before going to that, just we can have the refresher of what is the spatial filter. So as you can see, this is a particular image f of x comma y, and as per the conventions, the origin is always on the top left in the 2 dimensional image. Here is the x-axis, which are representing the number of columns. This is the y-axis, which are representing the number of rows. Now, for a particular pixel E onto the image, we want to define a simple 3 cross 3 neighborhood, and that particular 3 cross 3 neighborhood is defined as this. The original pixel images are A, B, C, D, E, F, G, H, and I. Now, we are interested in finding out the new value of this particular pixel E. Now, there is a 3 cross 3 filter, okay, which is having the coefficients as R, S, T, U, W, X, Y, Z. This filter is now being superimposed on this part of your neighborhood or this neighborhood of your image, and then the further process is basically a simple convolutional operation between the original pixel neighborhood and the filter. Okay, so the E process will be given by element multiplication and then addition. So this is similar to the convolutional operator which you are using in the digital signal processing, which was nothing but the folding, shifting, multiplication, and addition kind of a thing. Okay, so why we are talking about shifting? Because once the E process is calculated, the mask will then shift to the next column so that it will have the next neighborhood, and then this process will be repeated for all the pixels in the image until all the images are generated, all the pixels are processed rather. Okay, so now going into the sharpening filters, we must follow some kind of uh, uh, definitions, or we require some kind of you can say the points to be fulfilled for defining a particular spatial sharpening filter. So we require that the definition we use for the first order derivative, they must be zero in the flat segments. Now what do you mean by flat segments? These are the areas of constant grayscale. For example, if you can see on a blackboard, the blackboard is having the entire thing as green or black. So we say that this must be zero. Now why is it must be zero? Because the grayscale remains constant if you move from left to right, and if you take the derivative of a constant, it must be a zero. Okay, that means there is no change. Now it must be non-zero at the onset of a gray level step or a ramp. Now what do you mean by a gray level step or a ramp, that we are going to see with an example. Okay. So right now gray level step or a gray level ramp means if you are considering a particular grayscale, and if you see it is zero, that means black, and suddenly it moves to white. Now this is nothing but the gray level step. On the contrary, if the grayscales are becoming, or they are black and then they are gradually moving towards white, they are known as it is known as the gray level ramp. So 0 representing the black values, and 255 or 1.0 representing the white values. You are gradually moving from black to white. This is the ramp, and if you are suddenly moving from black to white, then this is be a gray level step. Okay. Now it must be non-zero along the ramps. Why it must be non-zero along the ramps? Because along the ramps there are continuous changes in your grayscales. As you can see that along the ramp, your grayscale is changing continuously. So that means the derivative should also be non-zero. A zero derivative represents a constant region. So along the ramps, it must be non-zero. Similarly, if you find out the second derivative, it must be zero in flat areas. Why? Because since the first order derivative is zero, the second order derivative is also going to be zero. It must be non-zero at the onset and the end of the gray level step or the ramp. Again, we have following the same definition of gray level step or the ramp. Now, whenever the gray level step is beginning, at that point the second order derivative must be non-zero, and similarly at the end the second order derivative must be non-zero. And the third point, which the second order derivative should follow, is that it must be zero along the ramps of a constant slope. Constant slope means delta x by delta, or delta y by delta x is equals to 1. That means the changes are becoming, or they are equal for every change, for every duration which we are going to consider for delta x. Now why does this happen? See, if this is a ramp, we generally represent it as by t. Okay, considering that the slope is 1, if you want to write down this formula of this line, then we will say that it is x of t is equals to t. And now if you take the first order derivative, the derivative of t would become 1, and the second derivative of 1 will again become 0. Okay, so it must be 0 along the ramps of a constant slope. Okay. So these are the conditions which sharpening spatial filter must follow. Whenever you are designing these filters, we must understand that these must be considered. So this is how we are going to find out the first and second order derivative of the differences. Now this is the difference in the x direction. So curly f by curly x, or rather if someone says it is del f by del x, it is equal to f of x plus 1 minus f of x. Now what is f of x plus 1 minus f of x? If you are considering this three-dimensional, sorry, because I'm using the mouse, I'm not able to write it down correctly. We say that this now this is your x-axis and this is your y-axis. So this is your f of x comma y. Okay, pardon the handwriting, because as I'm saying, I'm using the mouse and I'm not able to get this much. This is f of x comma y. Now here y index is missing, or they deliberately we are not used because we are just seeing it in the one direction. So this is f of x comma y. This is f of x plus 1 comma y. So this would be x plus 1 comma y, and similarly this would be x minus 1 comma y. Okay. So this is what will happen. Okay. Yeah. So I don't know whether you are able to see these notations or not. But then again, if f of x is considered to be the center pixel of the 3x3 neighborhood, the pixel which is located to the very right of this particular pixel is nothing but f of x plus 1, and to the left is nothing but your f of x minus 1. So in order to calculate the first order derivative, you have curly f by curly x is equals to f of x plus 1 minus fx. So that is the difference in one dimensions, and curly square x by curly x square f by curly x square, it is the second order derivative. So we'll have f of x plus 1 plus f of x minus 1 minus twice fx. So this is the second order derivative. Similarly, you can calculate the derivatives in the y direction. It will be curly f by curly y is equals to curly f of y plus 1 minus f of y, and curly square f by curly x square is equals to, so it would be f of x plus 1 plus f of x minus f of y plus 1 plus f of y minus 1 minus twice f of y. So that would be in the y direction. Now again, we can also always consider the difference as this curly curly f by curly x is equals to f of x minus f of x plus 1. We can do that. So what is this? F of x plus 1 minus f of x, this is known as the forward difference. And if you are taking f of x minus f of x minus 1, it would be known as the backward differences. So we can take any of them. It's not an issue. Okay. So now we are going to see the example of what is the special differentiation. So differentiation is the measure of the rate of change of function. Now let us consider this example. Now you can see this particular image. Now you can see that if if you can visualize a simple dot here, right? So this is a very bright spot in between this dark background. Okay. Now to the left of this, if we go out of the image and then we traverse from the image from the very left, and we come inside, you can see that this is a bright region, and slowly it is going into a darker region. It becomes black, then it suddenly becomes white when we touch this particular bright spot, and then it suddenly again becomes black. Then we move forward, and then there is a line which is a gray line. So gradually we go towards a little bit of gray, and then again we come to black. We stay in black, and then suddenly we go into the whiter region, and hence we can traverse out of the image. So what we are talking about here is this: if we are making a line from A to B, if you're making a line from A to B, this is what happens. Okay, again, so we are having the bright region here, and this region gradually goes into black, then it touches the brightest spot. So this is a very bright spot, so but the grayscale becomes very high. Then again it comes back to black, then goes to gray, and then again from black it goes to white here, and then it remains in white, and then it goes outside. So we know that black means the low levels and the white means the high levels. So this is what a gray level profile generally looks like. So here the gray level profiles, y-axis it is having 0 to 7, that means the number of gray scales. So the number of gray scales are from 0 to 7, 0 representing black, 7 representing white. So we can make out that it is a 3-bit image. Okay, because the maximum number of bits required to represent the highest grayscale, that is 7, is 3. So we say that it is a 3-bit image, and this particular profile is nothing but your image profile when we are traversing from A to B. So we can see that at A, which we are having some brighter region, and then gradually we are going towards the darker region. We enter the black region, and then suddenly we get an isolated point which is very sharp, and we get a high or bright point. Again we suddenly come down, and then we remain into the black region. Then gradually at this particular line, we are moving towards the a little bit gray level, and then again we are going to the black, and then suddenly we go to the white region, and then we remain in the white region. So this is the image strip which is representing the numerical information of this particular gray level profile 554321. So you can see that this is a ramp which is gradually moving from 54321. And there is isolated point, suddenly goes to 6, and then again there is a step. So from 000 it again goes to 777. Now we are going to calculate the first order derivative and the second order derivative. We know that how the first order derivative gets calculated: f of x plus 1 minus f of x. So for this particular point, what is f of x plus 1? For this point, f of x plus 1 is 4. So 4 minus 5, answer is minus 1. Right? Now for this point, this is f of x plus 1. So 3 minus 4, that is again minus 1. And similarly, we calculate for all the points. Second order derivative is calculated as f of x plus 1 plus f of x minus 1 minus twice f of x plus 1. So 4 plus 5, 9, minus 2 times 5 is 10. So 9 minus 10, answer is minus 1. Okay. And similarly, we will traverse to all these particular pixels. So now, what were our 6 assumptions which we did, or the 6 requirements for defining a derivative? The first order derivative should be non-zero along the ramps. So this is a ramp, and the first order derivative is non-zero. It should be 0 in constant region grayscale. So this is a constant region. We are having the 0, right? We are having the 0s. Here again, it's a constant region. We are having zeros. Again, this is a constant region. We are having 0. It should be non-zero at the onset of a ramp. So this is the onset of a ramp or a step. This is the onset. It is non-zero. It is the end. It is non-zero. It is the onset. And again, the first order derivative is non-zero. Okay. Now you see that this scale is actually not of a constant slope. So we are having different values here. The second order derivative should be 0 along the ramp of a constant slope. So this is the ramp of a constant slope. We are having zeros of a second order derivative here. And rest of the thing which we can identify or we can see from this point. So the first order formula is f of x plus 1 minus f of x, and these are the derivatives. And the first order derivative, this is the gray profile, and this is the first order derivative, how it behaves. So you can see that this is a gray scale isolated point. Now for this isolated point, how to find out at which point this definition is saying. So you can see that this graph is giving you a double line, and this double line is crossing your zero axis at somewhere. So this is the point at which there was a bright spot. Actually, the bright spot is here, right here, right? So it is here. Okay. Similarly, at the onset of a ramp or a step, it gives a response, a high response. Okay. The same thing will happen for the second order derivative also. Second order derivative, you can see that since there is an isolated point, it gives you a double edge. Okay. And this, but the point which you want to notice here is what was the response of the first order derivative to the isolated points. The isolated point represents the highest frequency component, right? Because it is changing very fast from black to white and then again to black. So this is plus 6 and then it is going to minus 6. Okay. Now what happens in the case of this 12? You can see here it goes to plus 6, then it goes to minus 12, and again then it comes to plus 6, and then it is 0. So the magnitude of the response, although negative, the magnitude of the response of the second order derivative to the high frequency component is very large as compared to the first order derivative, as you can see. Okay. The first order derivative is giving you maximum of 6 and minus 6. Here it is giving you minus 12. So it is responding to the high frequency component in a large manner, the second order derivative. Okay. So we generally use the second order derivatives for image enhancement. And why? Because it is having a stronger response to find details, as just we have seen. It is simple to implement, as we will see later on. And then once the second order derivatives are done, we are done with the second order derivative, we will look at the first order derivative. So the first sharpening filter that we are going to look at is the Laplacian. Now the Laplacian is having these particular properties. It is isotropic in nature. Now the isotropic filters are having the property that if you rotate the filter, the response of the filter to the image will not change. For example, there is a filter, you are rotating it to the amount of 90 degree. with the original filter, suppose the response is R1, and now you rotate the filter, you do the same process, and you find out that the response is R2. R1 and R2 will not have any kind of difference. So we say that this particular filter is isotropic in nature. Okay. Laplacian is one of the simplest sharpening filter, and the digital implementation is very easy. So this is what the Laplacian is. The Laplacian is defined as this particular thing. It is del square f is equals to curly square f by curly x square plus curly square f by curly y square. Now what is this curly square by curly f? It is the second order derivative in x direction. It is the second order derivative in the y direction. We know the definitions of the second order derivatives in first and second direction. Okay, so now we are introducing this y. Now you can see that this y remains constant for all the points because we are calculating the differences only in the x direction. Similarly, here we are having the x as constant because we are calculating the differences in the y directions. So now in order to get this formula, we need to add these two. So whenever we will add these two, we are having these four components which are non-identical. Well, these two components are identical, so they will have minus 4 times f of x, right? Something like this. F of x plus 1 comma y plus f of x minus 1 comma y plus f of x comma y plus 1 plus f of x comma y minus 1 minus 4 times xy. Now if you want to build this in the form of a mask, and I told you that x comma y is the center pixel. Now what's the coefficient of x comma y? It is minus 4. So we keep minus 4 in x comma y. Now what is f of x plus 1 comma y? This is the pixel. F of x plus 1 comma y. Here. What is the coefficient? Coefficient is 1. What is x minus 1 comma y? This is x minus 1 comma y. So here. What is the coefficient? Coefficient is plus 1. What is f of x comma y plus 1? This is f of x comma y plus 1. What is the filter coefficient? It is plus 1. What is the f of x comma y minus 1? This is f of x comma y minus 1. What is the filter coefficient? It is 1. So what is the filter? 0, 1, 0, 1 minus 4, 1 minus 4, 1, and 0, 1, 0. So this is the basic Laplacian filter. Simple. So it is very easy to implement. It is a two-dimensional filter. It is very easy to implement in the digital domain. And these are the variations. You can see here. 0, 1, 0, 1 minus 4, 1, 0, 1, 0. And you can invert it also. As I told you, if you're taking the backward differences, the center pixel will become positive and the rest of the pixels will become negative. So now these Laplacians, these two Laplacians, are only considering the immediate neighbors. This is also another variation of Laplacian, which are considering the diagonal elements also. So these are the diagonal neighbors of this pixel, center pixel. Okay. So this is minus 8 in the center, and all the plus 1. This is positive 8. This is minus 1. One thing you should note that if you add up all the coefficients of the filters, let it be this, or this, the sum of the elements will become 0. Now, why it will become 0? This is a very important question which you should understand. It should become 0 because in the area of constant grayscales, the response of a high pass filter should be 0. That means if I put this filter on the image or in the area of an image which is having all the constant grayscales, my response of the filter should always become 0. And if the coefficients around, or if the sum of the coefficient of this filter is non-zero, then the answer will also be non-zero, representing that there are some high frequency components which is a false positive. Okay. So that's why whenever you're designing a high pass filters spatial domain, you must take care that the coefficients should always be 0. Remember, we are soon going to see a filter in which the coefficients, summation of the coefficient will not be 0, but that is not actually the high pass filter. That would be the enhancement filter. So don't get confused between that. Now see here. Now if I rotate this filter by 90 degrees, 90 degrees means this pixel will come here. This pixel will come here. Okay. So if I rotate this by 90 degree, the filter response will not change. But if I rotate it by 45 degrees, for example, this pixel comes here, this pixel comes here, this pixel comes here, then the response of this filter is going to change. So these filters are isotropic filters, but the isotropicity is for 90-degree rotations. While for these filters, you can either use 90-degree rotations or you can do 45-degree rotations, whatever it is. So these filters are more isotropic as compared to these particular filters. Now, these filters are going to give us the high frequency components. Now, in order to enhance the image, we want to add these high frequency components to the original images. And there are two basic formulas in which we are going to use for enhancement. The first formula is either we can subtract the result of the uh, Laplacian from the original image, or we can add it to the Laplacian of the we can add the Laplacian to the original image. When we will subtract, when the center of coefficient of the Laplacian is negative, we are going to subtract. When it is positive, we are going to add. We'll see how it happens. So here it is. See, this is the original image, and this is the means the result of the Laplacian of the image. Now here we have scaled this Laplacian so that it is visible onto the image. So you can see that here in this Laplacian, we are having all the fine details of this moon. Okay, you can see the borders of the craters and the border of the moon itself and all those things. So high frequency components are visible. Yeah. Now since uh, we have used the negative centered filter, negative centered filter, we are going to subtract this from the original image. So when, and this is the original image, and we are now subtracting the Laplacian's filtered image, we are having the sharpened image. So when you compare these two, you can very easily see that the high frequency components are very much visible here. So this image is obviously much more enhanced as compared to the original image. You can see it clearly here. All the high frequency components which were suppressed in the original image are now becoming very visible here, basically. So this is how the Laplacian is used for image enhancement. So finding the Laplacian is the process of the high frequency component, and then either subtracting or adding the Laplacian to the original image will represent the image enhancement process. So this is what we do: f of x comma y minus the Laplacian. So f of x minus x comma y minus all this. So basically what we are doing two operations. First of all, we are having the original image, we find out the Laplacian, and then we subtract the Laplacian from the original image. And this entire expansion will result into this: pi f of x comma y minus f of x plus 1 comma y minus f of x minus 1 comma y minus f of x comma y plus 1 minus f of x comma y minus 1. Again, you can put this into the filter combination, and you can see here it would become like this. So what is the coefficient of f of x comma y? It is 5. Okay, so center is 5. What is the coefficient of f of x plus 1 comma y? It is minus 1. Okay, so the coefficient becomes minus 1. So now we are having a new filter which is similar to the Laplacian filter, but instead of plus 4, we are having a plus 5 in the center. So what this filter does, it eliminates the step of Laplace of finding out the Laplacian and then adding or subtracting from the image. It directly do the image enhancement. So this is the enhancement filter. It is not the high pass filter. It is not the sharpening filter. It is the enhancement filter. And hence you can see that the sum of the elements of sum of all the elements of the filter is not 0. It is 1, positive 1. And as I told you previously, the sharpening filters must have the sum of the elements as 0. This is the enhancement filter, and hence the sum of the element is not equal to 0. So don't get confused between the enhancement filter and the sharpening filter. And again, Laplacian itself is not an enhancement filter, it is a sharpening filter. Laplacian, when used onto the original image, will result into the enhancement or the enhanced image. Okay, so again, you can see here the high frequency components are much clearly visible when we are doing the image enhancement. Okay, so for this particular variation of Laplacian, in which the center pixel is 8 and we are considering all the diagonal neighborhoods, the enhancement filter looks like this. Okay, so it is very obvious, you can calculate it on your own again. So for students, this is all about what Laplacian is and how do you do the image sharpening, and then how the sharpened uh, image or the sharpened result is used for the process of image enhancement. So again, to go to the brief, what we have seen is that we must have the these particular conditions to be satisfied for a sharpening filter. The sharpening filters are represented by the differentiation, and we can have differentiation in x direction and differentiation in y direction, and then we can find out how to find out the Laplacian. There are two basic forms of Laplacians, one which is considering the immediate neighborhoods only, and one which are considering all the neighborhoods. Okay, and then after finding out the Laplacian, we are going to either add the Laplacian to the image, or we are going to subtract the Laplacian of the image based on the center coefficient which we have used, and that will result into the enhanced image. Okay, So hope you found this lecture useful and interesting. I will see you later on for some other kind of a lecture. Thank you and goodbye.